Good evening, everyone. Welcome to week 7 assignment solving session. Today I'll be discussing questions related to week 7 lecture materials and week 7 assignment solution. So let's start. The first question is, according to Wade's rule, TeB9H11 is an example of option A is rosoborane, B is nidoborane, C is arachnoborane, and D is hypoborane. So by using Wade's rule, we will be able to predict structure of boron hydrates. First, we will have to determine total number of valence electron. 3 electron will be provided by each boron and 1 electron provided by 1 hydrogen. Then we will have to subtract 2 electrons for each BH unit, and the remaining number of electrons is divided by 2, which will give skeletal electron pair, which determines the type of cluster. Here we are asked to find cluster type of TeB9H11. When heteroatom is present, we can replace it with appropriate BHN unit. Here Te is given, which is in the group of oxygen. So one Te is equivalent to one BH3 unit. So in TeB9H11, we can rewrite it as BH3, that is for represents Te, then B9H11. So it will become B10H14. So when we apply Wade's rule here, we can calculate the total number of valence electrons, that is 10 into 3, which is the electrons from boron, plus 14 into 1, that is 14 hydrogen is present, each hydrogen provides 1 electron, then minus 10 into 2, which corresponds to each BH unit. So SCP will be 30 plus 14 minus 20 divided by 2, which is equal to 24 by 2, which is 12. So SCP is equal to n plus 1. So here we have 12. So n corresponds to 11. And when n is 11, that will be closer. But we have B10 here. So n minus 1 will be 10. That will become nidoborane. So it will occupy 10 vertices of the nido structure. So the answer is option B, nidoborane. Next question is, according to Wade's rule, CpB10H11 is an example of option A is closoborane, B is nidoborane, C is arachnoborane, and D hypoborane. So similar to previous question, we have to calculate skeletal electron pairs first. So in CpB10H11, C is equivalent to BH unit and P is in the group of nitrogen, so it will be equivalent to BH2. So we can rewrite CpB10H11 as BH, BH2 and B10H11. So that will become B13, B12 and H3H here and 11H in this group. So that will be 14. So can calculate the SCP. Will be 12 into 3 from each boron plus 14 into 1 from each hydrogen minus 12 into 2 from each BH unit divided by 2. That will be 36 plus 14 minus 24 by 2 equal to 13. So SCP is 13, which is n plus 1, and n will be 12, which will be closer. So we have B12H14, so n is 12, so it's a closure boron. Next question is, which of the following is isostructural to Pb4 2 minus? Option A is C2B3H7, B is C2B5H9, C is C2B3H5, and D is C2B4H8. So we can apply Wade's rule here and find out the SCP and structure and compare with that of the given option. So in Pb4 2 minus, lead is in the carbon group, so we can rewrite Pb as BH. So Pb is equivalent to BH. So Pb4 will be 4 times 2 minus will become BH 4 times 2 minus. So that will be B4 H4 2 minus. So when we apply Wade's rule, SCP will be 4 into 3 plus 4 into 1 because 4 hydrogen are there and 4 boron are there minus 4 into 2 because 4 BH units divided by 2 will be 12 plus 4 plus there is a 2 minus charge here, so we'll have to add that as well here. Plus 2 minus 8 divided by 2, that will be equal to 5, which is n plus 1. So n plus 1 for this B4H4 2 minus is 5, so n equal to 4. So n equal to 4 means here also it's B4. So Pb 4 times 2 minus will be closer. And in option A, it's C2B3H7. So 1 C is equivalent to 1 BH. So BH 2 times because 2 carbon is present, then B3H7. So when we calculate total B and H, it will be B4, 3 and 2B, that will be B5, then H9, and SCP equal to 5 boron, 5 into 3 plus 9 hydrogen, so 9 into 1, then no charge is present, and 5 BH units, 5 into 2 divided by 2, that is equal to 15 plus 9 minus 10 divided by 2, that is 7, which is the n plus 1, and n will be equal to 6. But we have B5. So n equal to 6 will be closure. But what we have is n equal to 5. So that is n minus 1 equal to 5. That will be nidoborane. So this one is nido. Here 2C is present. So BH twice B5 H9. That is B7 H11. So SCP equal to 7 into 3 for boron, 11 into 1 for hydrogen, then 7 BH units divided by 2 equal to 21 plus 11 minus 14 divided by 2. That will be equal to 9, and which is n plus 1, and n equal to 8 will be closure, n minus 1 will be 7, which is nido. So we have B7, so it is nido. So here C2 is present, BH2, BH twice, then B3, H5, that is B5, H7. So SCP equal to 5 into 3 for boron, 7 into 1 for hydrogen, and 5 into 2 for BH unit divided by 2, which is equal to 15 plus 7 minus 10 by 2, which is equal to 6, which is n plus 1, and n equal to 5 is closure. So we have 5 here, so this compound is closure. And the last one, here BH twice, B4 H8, that is B6 H10. So SCP equal to 6 boron is present, 10 hydrogen, minus 6 BH units. So that is 18 plus 10 minus 12 by 2, which is equal to 8, which is the n plus 1. And if n equal to 7, that is closure. We have n equal to 6 here. So that is n minus 1 equal to 6, that is nido. So this compound will be nido. So the question was, which is isostructural to Pb4 2 minus? We have Pb4 2 minus is closure. So in the given options, only one is closure, which is option C. Next question is SB9H9 and SB9H12 minus are the examples of option A, closure and nido heteroboranes, B is nido and arachno heteroboranes, C is closure and arachno heteroboranes, and D, nido and closure heteroboranes. So heteroboranes are boranes having one heteroatoms. Here it's sulfur, and sulfur is present in the oxygen group. So boron carbon, nitrogen, and oxygen. That's the order in the periodic table. So carbon is BH, nitrogen is BH2, and oxygen is BH3. So we can represent oxygen and its group members as BH3. So first we can calculate CP for Sp9H9. So Sp9H9 to BH3 for sulfur and B9H9 for the rest of the B9H9, and it will be represented as B10H12. So calculating SCP, there are 10 boron, 10 into 3 plus 12 hydrogen and 10 BH2 groups. That is 30 plus 12 minus 20 divided by 2, which is equal to 11, which is n plus 1, and n will be 10. So if 10 borons are present, it will be close boron. So this one is close. And next one is Sb9H12 minus. So here BH3 and B9H12 minus, that will be B10H15 minus. So B10H15 minus, the Cp will be 10 into 3 plus 15 hydrogen minus 10 BH groups. It is 30 plus 15. So one electron is present as negative charge. So then we have to add that as well. So it will be 30 plus 15 minus 20 plus 1 divided by 2, which is equal to 13, which is n plus 1, and n equal to 2 is n equal to 12 will be close. So n equal to 11 will be nido, and we have here 10. So uh, n equal to 12 is close. So n minus 1 equal to 11 will be nido, and n minus 2, that is 10, that will be arachno. So we have B10, so it is arachno group. So option C is the answer. Sb9H9 will be closo, and Sb9H12 minus will be arachno. Next question is, according to Wade's rule, SN9 2 minus is an example of Option A, chloso, B, nido, C, arachno, and D is hypho. So, Sn is in the group of carbon. So, we can replace Sn by 1 BH. So, Sn is equivalent to 1 BH. So, Sn 9 times 2 minus will be equivalent to BH 9 times 2 minus, which is B9 H9 2 minus, and SCP will be 9 borons plus 9 hydrogen plus 2 negative charges minus 9 BH groups divided by 2. That is 27 plus 9 plus 2 minus 18 divided by 2, which is equal to 10, which is the n plus 1. N equal to 9 will be close. So we have B equal to 9. So the structure is closed. The next question is, with respect to the following statements, the correct option is or are statement 1, both diamond and graphite are good conductors of electricity. Second one is density of diamond is greater than graphite. Third one is all carbon atoms in diamond are sp3 hybridized, and this interlayer distance between two graphene sheets is 360 picometer. So the statement 1, both diamond and graphite are good conductors of electricity. This statement is incorrect because uh, diamond do not conduct and it has an sp3 hybridized carbon with tetrahedral geometry, and in graphite the carbon is sp2 hybridized and one electron is present in unhybrid p orbital, which is responsible for conduction. And second statement, density of diamond is greater than graphite. So this statement is correct. Diamond has density of 3.513 gram per centimeter cube, and for graphite the density is 2.26 gram per centimeter cube. So this statement is correct. And option 3, all carbon atoms in diamonds are sp3 hybridized. So this statement is correct. In diamond, all carbon atoms are sp3 hybridized and has cubic structure where carbon atoms are present at corners and face centers and present in alternate tetrahedral voids. And so this statement is correct. And last statement is interlayer distance between two graphene sheets is 360 picometer. So this statement is wrong. The interlayer distance between two graphene sheet is 335 picometer. So this statement is wrong. So the correct option is statement 2 and 3 are the correct ones. The next question is dehydration of malonic acid using P4O10 gives option A C4O3, option B C3O2, option C is C2O3, and D is C2O4. So this is the method for synthesis of carbon suboxide. So carbon suboxide is C3O2. Malonic acid is CH2 COOH twice. So when it is treated with P4O10, water is removed to form carbon suboxide, which is C. So it is C3O2. And its boiling point is 279 Kelvin. And the CC double bond will be 125 picometer, and C double bond O is 115 picometer. So the answer is option B, C3O2. The next question is controlled addition of bromine into C60 at 298 Kelvin in benzene or CCl4 affords. Option A, C60Br24, B is C60Br6, option C is C60Br60, and option D is C60Br66. So C60 can be functionalized with halides by various methods, and the reaction of controlled addition of bromine into C60 at 298 Kelvin in benzene or CCl4 will give C60Br6. So C60Br6 will be the product formed from this reaction, and we can form chlorinated and fluorinated variants as well. So those reactions are C60 when treated with ICL in ICL and 298 Kelvin. So when C60 is treated with ICL at 298 Kelvin, we will get in the presence of C6H6 benzene, it will give C60Cl6, and in the presence of fluorine and 343 Kelvin, if we do the reaction for so many days, it will give C60F60, and when we treat this with Br2 at 298 Kelvin, it will give C60Br24, and then if we use Br2 and at 298 Kelvin in presence of CS2 and or CHCl3, it will provide C60Br8, and finally in reaction with again F2 in presence of sodium fluoride at higher temperature 520 Kelvin, it will give C60F46. The next question is the point group of carbonate ion CO3 2- is option A is D3H, option B is C3V, option C is C3H, and option D is C2V. So CO3 2-, that is a carbonate ion. It has a trigonal planar structure. It is C double bond O, O-, and O-. Two negative charges are present, but they will go into resonance and it can form CO- and double bond O and O-, and again this can undergo resonance and it will become O-, double bond O and O-. So all these are possible. So we can write it as C with, so we can write it like this because the bond lengths will be equivalent. And so since this is a planar and the negative charge is delocalized, when we have a molecule that is a trigonal planar geometry which has high symmetry, they are in D3H point group. So in D3H, there will be three vertical plane sigma v and three C2 axis will be present. One horizontal mirror image will be present. Then two C3 axis will be present. Then there will be identity and two S3 will be present. So this you will be familiar on these notations in group symmetry. So if you don't know it, so that's not an issue. So if we have a planar molecule with high symmetry like BF3, BCl3, etc. So all these have central atom, uh, a central atom and highly symmetric atoms at the end. So it will be planar with same atoms at the occupying all three corners. So it will be D3H. So answer is option A. Next question is the reaction of CS2 with RHCl PPH3 thrice gives. Option A is RHCl CS2 PPH3 twice and PPH3 double bond S. Option B is RHCl eta 1 SC PPH3 twice and PPH3 double bond S. Option C is RHCl eta 1 CS PPH3 twice and PPH3 double bond S. And option D is RHCl eta 2 CS PPH3 twice and PPH3 double bond S. So here the notation eta represents the number of electrons provided by the ligands. So here Sc implies the sulfur is coordinated to RHCl PPH3 twice through sulfur and it provides only one electron. Here it's eta 1 CS, which means this CS is coordinated through carbon and it gives only one electron. And here it's eta 2 CS, it means it is coordinated to rhodium through carbon and it gives two electrons. So what we have is RHCl PPH3 thrice and reaction with CS2. So we have to write this molecule first. It is RH at the central metal, then chlorine and PPH3 three times. So when it's reacted with CS2, one PPH3 will be removed. So it will form RH, Cl, PPH3 and C double bond S and S. It will coordinate like this. And this PPH3 will come back and react with this sulfur. So it will be RHCl PPH3 PPH3 and CS. So one of the carbon sulfur bond will be broken and it will form bond with PPH3. So the answer is option C, RHCl eta 1 CS, PPH3 twice and PPH3 double bond S. The next question is IR4CO12 times is an example of option A, chloro cluster having TBP geometry, option B, nido cluster with tetrahedral geometry, option C, nido cluster with trigonal pyramidal geometry, and option D, hypocluster with square planar geometry. So when we apply Wade's rule in metal carbonates, one MCO3 unit can be considered as similar to one BH unit. So IR CO 3 times. This will be 1 unit. So we have IR4 CO12, which means that there are 4 IR CO 3 times units. And number of cluster bonding electrons is given by the equation X equal to mu plus n minus 12, where mu equal to number of valence electrons from metal atom, and n equal to number of electrons provided by one ligand. So in IRCO 3 times, iridium will be having D7S2 configuration. So that will be 9 electron given by one iridium, which is new. And CO is having it provides 2 electrons to the metal center, and there are 3 CO in IRCO thrice. So that will be 3 into 2 equal to 6 electron is the N. So we can calculate X 9 plus 6 minus 12. That is equal to 3 electrons. So that means this one is for IRCO thrice. So one IRCO3 gives 3 electrons. So we have 4 units for IRCO thrice. That means 4 into 3, that is 12. So skeletal electron pairs will be 12 by 2, which is 6, which implies n plus 1. So we have n plus 1 equal to 6, and equal to 5 will be closure, and n minus 1 will be 4, which will be nido. We have 4, so 4 is nido, and n equal to 5 means that will be TBP, trigonal bipyramidal, and when we have n minus 1, that means one of the vertices will be removed from. So if these are the vertices of TBP, one will be removed. So that will be tetrahedral remaining. So n equal to 4 will be nido, and it will have tetrahedral geometry. So option B is the answer. Next question is, among the following, the incorrect statement for magnesium boride is option A, it loses its electrical resistance when cooled. Option B, it has simple structure in which boron atoms are arranged in graphite-like planes. Option C, magnesium atom donates one valence electron to the network of boron atoms. Option D, it has superconducting properties. So, the first statement, it loses its electrical resistance when cooled. So, this statement is correct because MgB2 is used as a superconducting materials. Superconductor. So, what is a superconductor? The material which will have almost zero resistance at lower temperatures. So, it will conduct highly, which is having low resistance. So, the statement 1 is correct. It loses electrical resistance when cooled. And option B, it has simple structure in which boron atoms are arranged in graphite-like planes. So the statement is true. Boron atoms are in graphite-like planes, and in next layer, magnesium atoms are present. So the structure is given here. So this hexagonal structure, which has the graphene-like layer, it is formed by boron atoms, and the red ones are magnesium. And option C, magnesium atom donates one valence electron to the network of boron atoms. So this statement is incorrect because one magnesium atom will donate 2 electrons to the network, because magnesium is S2 configuration and it can go to Mg2 plus configuration by giving 2 electrons to the boron atoms. So this statement is wrong. And option D is it has superconducting properties, which is correct because it will have almost zero resistance at low temperatures. So the answer is option C, which is the incorrect statement. The next question is, most promising boron containing compounds for boron neutron capture therapy BNCT are option A, Na2B12H11SH and Na2B12H11, B is Na-B12H11SH and Na2B12H12. Option C is Na2B12H11SH and Na2B12H12, and option D is Na2B12H11SH and Na-B12H12. So, boron neutron capture therapy, which is BNCT, it involves injecting B10 labeled boron compounds which preferentially binds to tumor cells. And when we irradiate with neutrons, the B10 undergoes nuclear fission and produces a helium nucleus and lithium plus nucleus. And this process liberates very high energy. So the reaction will be B10 plus 1 neutron giving helium plus lithium ion. So the boron containing compounds used for this purpose are polyhedral borohydrates like Na2, B12H11SH and Na2B12H12. So option C is the answer. The next question is, predict the outcome of the following reactions. First reaction is BF3 dot NME thrice plus BCl3. 2 is BCl3 NME thrice plus BF3. Third option is BH3 SME2 plus ME3. And fourth option is BF3 NME thrice plus SME2. So what we have to know is that Lewis acidity and Lewis basicity of each of the uh, compounds. That if we want to know if this reaction will proceed or not, we need to know the Lewis acidity order of BCl3 and BF3. So in BF3, because of the similar energy of boron and fluorine uh, p orbitals, there will be a back donation to the boron. So the Lewis acidity is low in BF3 compared to BCl3. So the BCl3 is highly Lewis acidic compared to BF3. So this reaction will proceed and will give the product BCl3 dot NMe3 plus BF3, because this one is less Lewis acidic compared to BCl3. And here BCl3 and NMe3 plus BF3. So this reaction will not proceed. So no reaction because BCl3 is highly Lewis acid. So this bond between this acid and base will be stronger compared to BF3 and base. And next one is BH3 SME2 plus NME thrice. Here this NME thrice is highly Lewis basic and SME twice is weak Lewis base. So when we react a BH3 with weak Lewis base and a strong Lewis base, the strong Lewis base and BH3 will react. So that will give BH3 dot NMe thrice plus SME2. And here BF3 and strong Lewis base is reacted with SME2, which is a weak Lewis base. So the reaction will not proceed. So there is no product formation. So the answer is option D. First product is BCl3 and NMe3 and BF3. In the second reaction, there won't be any product. Option C is in the third reaction, BF3 and NMe3 is formed with SME2 will be replaced. And in the fourth one, there won't be any reaction between BF3 and NMe3 and SME2. The next question is, according to Wade's rule, PB9H11 minus is an example of option A, closoborane, option B, nidoborane, option C, arachnoborane, and option D, hypoborane. So P, which is phosphorus, it's in the nitrogen group. So we can replace P with BH2. So when we rewrite this whole one, P B9H11, we can rewrite as BH2 for phosphorus, then B9H11. That will form total 10 boron, and there is a negative charge, then H13. So there is 10 boron is present, so 10 into 3 for each boron. Then 13 hydrogen is present, 13 into 1 for 13 hydrogens. Then how many BH units? There are 10 BH units present, so 10 into 2 for each BH unit. Divided by 2 will be the SEP. So SEP equal to 30 plus 13, we'll have to add one this negative charge, which is plus 1 minus 20 divided by 2, which will be equal to 12, which is n plus 1. So n plus 1 equal to 12, n equal to 11 means it's a closed structure. We have 10 boron, so that is n minus 1, which is 10, which will be nidoboron. So the compound PB9H11 minus is nidoboron. So option B is the answer. Next question is the example of nidocarburin is option A C B6H12, B C3B6H12, C C2B4H6, and option D C2B4H8. So we can replace carbon with BH unit. So we can go for C B6H12, that will be BH B6H12, that is equal to B7H13. So SCP will be 7 into 3 for boron plus 13 hydrogen minus 7 BH units are present. That is equal to 21 plus 13 minus 14 divided by 2, which is equal to 10, and equal to n plus 1, and here n plus 1 equal to 10, so n equal to 9 will be close of, but we have 7, which implies n equal to 8 will be nido, and n equal to 7 will be arachno. So this one is arachnoborane. And next one is C3B6H12. So BH thrice and B6H12, which is equal to B9H15. So SCP will be 9 into 3 plus 15 into 1 minus 9 into 2 divided by 2 will be the SCP. So 27 plus 15 minus 18 divided by 2, which is equal to 12. So n plus 1 is 12 and n equal to 11, but we have 9 borons, and n minus 1 equal to 10, that will be nido, and n minus 2, which is 9, that will be arachno. So this one is arachnoborane. Next one is C2B4H6, that is BH2 and B4H6, that is equal to B6H8. Skeletal electron pairs will be equal to 6 into 3 plus 8 into 1 minus 6 BH units. 6 into 2 divided by 2, which is equal to 18 plus 8 minus 12 divided by 2, which is equal to 7. So n plus 1 equal to 7, which means n equal to 6 is closer, and we have B6, so this one is closer. And last one is C2 B4 H8, means BH twice B4 H8 equal to B6 H10. So SCP equal to 6 into 3 plus 10 into 1 minus 6 BH units, that means 6 into 2 divided by 2, it will give 18 plus 10 minus 12 divided by 2, which is 8 equal to n plus 1. So n plus 1 equal to 8, n equal to 7 will be closer, but we have p equal to 6, so n minus 1 equal to 6, which will be nidoborean. So we were asked to find the example of nidocarpellane. So option C, which option D, which is C2B4H8, it has the nido structure. The next question is, the following statements are given with respect to graphite. Statement 1 is graphite consists of stacked one-dimensional carbon sheets. Second statement is oxidizing agents or reducing agents may be interconnected between these sheets with concomitant electron transfer. Third statement is single layer of graphite is called as graphene. And fourth one is graphite reacts with hot concentrated sulfuric acid to give a non-aromatic compound C6CO twice H6 times. So the first statement, graphite consists of stacked one-dimensional carbon sheets. So the statement is incorrect because the carbon sheets in graphite is in 2-dimensional. So it's given 1-dimensional. It's not correct. It's 2D sheets. And second statement is oxidizing agents or reducing agents may be intercalated between these sheets with concomitant electron transfer. So the statement is correct because we can prepare Kc8 and Ca6 times, that is potassium and calcium intercalated graphenes. So this one can be prepared by potassium vapor reacting with graphite sheet at heating at 300 degrees Celsius. So it will give Kc8. And so the second statement is true. And the third one, single layer of graphite is called as graphene. So this statement is also true. And fourth statement, graphite react with hot concentrated sulfuric acid to give non-aromatic compound C6CO2H6 times. So this statement is not correct because the compound C6CO2H H6 times, which is called as miltic acid, and it is an aromatic compound. So the compound is having a benzene structure, COH replacing each hydrogen in benzene. So the answer is option C. Second and third statements are correct. The next question is graphite on heating with potassium at 300 degrees Celsius gives option A KC60, option B KC36, option C KC24, option D KC8. So when we heat graphite with potassium at 300 degrees Celsius, it will give KC8. And from KC8 we can prepare KC24, 36, 48 and 60 by subsequent heating. So from KC8 when we heat it, it will give KC24, then heating will give KC36 and again heating will give KC48 and finally it will give KC60. So this one is having copper color and KC60 will be having blue color. The next question is C60 has how many pentagons and hexagons? So option A is 14 pentagons and 18 hexagons. Option B is 12 pentagons and 20 hexagons. Option C is 10 pentagons and 20 hexagons. Option D is 12 pentagons and 18 hexagons. So the answer is 12 pentagons and 20 hexagons. So each this blue colored one is pentagons and the pink color are hexagons. So total there will be 12 pentagons and each pentagon will be surrounded with 5 hexagons. So total of 12 pentagons and 20 hexagons are present. Next question is according to Wade's rule, GE9 4- is an example of option A closoborane, B nidoborane, C arachnoborane and D hypoborane. So germanium is in the carbon group, so it can be replaced with BH. So 1 GE is equivalent to 1 BH group. So BH 9 times 4-, that will be B9 H9 4-. So we can write down the STP. So it will be 9 into 3 plus 9 into 1 for hydrogen plus 4 negative charge minus 9 BH units, 9 into 2 divided by 2. It will be 27 plus 9 plus 4 minus 18 divided by 2. That's equal to 11, which is n plus 1. And n equal to 10 means it's a closoborane. N minus 1, which is 9, will be equivalent to nidoborane. So we have B9, which is n minus 1, it's a nidoborane. So if we have B9, if we have GE9 2 minus, that will be having closer structure. But we are given GE9 4-, it has nido. The next question is how many isomers are possible for GE5H12? So this is similar to the compound C5H12, which is pentane. So it is similar to uh, pentane only. So if we write in stick formula, it will be 5 germanium. So 1, 2, 3, 4, 5. So this one is one isomer. Then it can be like this, and so 3 isomers will be possible. We can number it 1, 2, 3, 4, 5 germanium. So 3 isomers are possible for Ge5H12. Next one is Si6H14. So again, it's similar to C6H14. So 1, 2, 3, 4, 5, 6. This one, then 1, 2, 3, 4, 5, and 6. And 1, 2, 3, 4, 5, 6. Next one is so 5 different isomers are possible for Si6H14. So that's all for today. If you have any doubt, you can ask.